What specific problem does the proposed method, Stylus, aim to solve in the context of generative image models?
The proposed method, Stylus, aims to solve the specific problem of efficiently selecting and composing relevant adapters based on user-provided prompts in the context of generative image models. Stylus addresses the challenges of retrieving and merging multiple low-rank adapters, LoRa, to enhance the capabilities of foundational models for image generation. It automates the process of assessing user prompts to retrieve and compose sets of highly relevant adapters, thereby augmenting generative models to produce diverse sets of high-quality images. Stylus tackles issues such as efficiently converting adapters into lookup embeddings, segmenting user prompts into distinct tasks, and avoiding the degradation of image quality, introduction of biases, and concept overrides that can occur when composing multiple adapters. The system employs a three-stage framework: refine, retrieve, and compose, to refine adapter descriptions, retrieve relevant adapters based on user prompts, and compose them into tasks, ensuring semantic alignment and avoiding biases detrimental to image generation. Stylus also introduces a masking strategy to control the number of adapters per task, promoting image diversity and minimizing the risk of undesirable effects from composed adapters.
How does the proposed method, Stylus, work? Illustrate step by step.
The proposed method, Stylus, works through a three-stage framework that addresses the challenges of selecting and composing relevant adapters based on user prompts. 1. Refiner. The first stage involves the refiner, which generates textual descriptions of an adapter's task and computes text embeddings for retrieval. It uses a vision language model to improve descriptions and an embedding model to generate embeddings for all adapters. 2. Retriever. The retriever fetches the most relevant adapters by processing the user prompt and calculating cosine similarity scores between the prompt's embedding and each adapter's embedding. The top K adapters with the highest similarity scores are selected. 3. Composer. The composer segments the prompt into tasks and assigns retrieved adapters to each task based on similarity scores. It filters out irrelevant adapters and those likely to introduce biases. The composer applies a binary mask to control the number of adapters per task, ensuring image diversity and minimizing undesired effects. Overall, Stylus efficiently assesses user prompts to retrieve and compose sets of highly relevant adapters, automatically augmenting generative models to produce diverse sets of high-quality images. The method leverages a vision language model, text encoders, and a composer stage to enhance image generation by selecting, retrieving, and composing adapters tailored to user prompts, ultimately improving visual fidelity, textual alignment, and image diversity over existing checkpoints.
What are the theoretical or practical benefits of using Stylus compared to existing retrieval-based systems for selecting and composing adapters?
The theoretical and practical benefits of using Stylus compared to existing retrieval-based systems for selecting and composing adapters are significant. The Stylus system introduces a three-stage framework, refine, retrieve, and compose, that addresses the challenges of efficiently retrieving and composing relevant adapters based on user prompts. Stylus employs a refiner to generate textual descriptions and embeddings of adapters, a retriever to fetch the most relevant adapters based on similarity metrics, and a composer to segment prompts into tasks and assign retrieved adapters to each task. This approach ensures that only highly relevant adapters are selected and composed, leading to improved visual fidelity, textual alignment, and image diversity. Stylus outperforms existing retrieval-based systems by efficiently assessing user prompts to retrieve and compose sets of highly relevant adapters, automatically augmenting generative models to produce diverse sets of high-quality images. The composer in Stylus filters out irrelevant adapters that are not semantically aligned with the prompt and detects those likely to introduce foreign bias, ensuring that only suitable adapters are selected and composed for each task. Additionally, Stylus applies a binary mask to control the number of adapters per task, leading to highly diverse images and minimizing the risk of composed adapters introducing undesirable effects to the image. In practical terms, Stylus improves the efficiency and effectiveness of adapter selection and composition, resulting in better image quality, reduced biases, and increased image diversity. The system's performance gains are demonstrated through human evaluations, automatic benchmarks, and comparisons with existing retrieval methods. Stylus also presents a practical solution that does not impose large overheads on the image generation process, making it a viable and efficient tool for various image-to-image applications, such as image translation and inpainting.
How is the method, Stylus, validated or tested in the paper?
The method, Stylus, is validated and tested in the paper through a comprehensive experimental setup. The authors introduce a dataset called Stylus docs, consisting of 75K loris with pre-computed embeddings and improved adapter descriptions from the refiner component of Stylus. They evaluate Stylus against the stable Diffusion v1 5 baseline model using two well-known checkpoints, Realistic Vision v6 and Counterfeit v3. The evaluation includes human evaluation, automatic benchmarks using clip and FID metrics, VLM as a judge for textual alignment and visual fidelity, diversity per prompt assessment using Diffeed and GPT-4V metrics, comparison with alternative retrieval-based methods, and breakdown of Stylus's inference time. The human evaluation involves 4 users assessing 150 images from Stylus and stable Diffusion v1. 5 for each dataset checkpoint combination. The automatic benchmarks assess the correlation between generated images and user prompts, clip, and evaluate the diversity and aesthetic quality of image sets, FID. The VLM is used to assess textual alignment and visual fidelity. The diversity per prompt is evaluated using Diffeed and GPT-4V metrics. Stylus is also compared to different retrieval methods, including random, retriever, and re-ranker. Additionally, the breakdown of Stylus's inference time is provided to understand the latency introduced by various components of Stylus during the image generation process. Finally, Stylus's applicability across different image-to-image tasks like image translation and inpainting is demonstrated with examples.
What results were achieved with Stylus in terms of visual fidelity, textual alignment, and image diversity compared to the stable diffusion checkpoint?
Stylus achieved significant improvements in visual fidelity, textual alignment, and image diversity compared to the stable diffusion checkpoint. In terms of visual fidelity, Stylus improved the quality of images by generating highly detailed and specific elements as per the user prompt, as evidenced by human evaluations showing a preference for Stylus over existing model checkpoints. This improvement was also supported by automatic benchmarks such as FID, which evaluates the diversity and aesthetic quality of image sets, showing that Stylus shifted the clip-FID Pareto curve towards greater efficiency. Additionally, Stylus demonstrated better textual alignment, with negligible differences compared to the stable diffusion checkpoint, indicating that Stylus did not introduce additional artifacts. Moreover, Stylus excelled in image diversity, generating highly diverse images due to different composer outputs and masking schemes, as shown by metrics like Diffeed and GPT-4V scores. Stylus prevailed in approximately 60% and 58% of cases for Diffeed and GPT-4V, respectively, showcasing its ability to produce more diverse images consistently. Overall, Stylus outperformed the stable diffusion checkpoint in terms of visual fidelity, textual alignment, and image diversity, making it a superior choice for generating high-quality and diverse images.
What are the limitations or drawbacks of using Stylus for automating the selection and composition of adapters for image generation?
The limitations or drawbacks of using Stylus for automating the selection and composition of adapters for image generation include the potential degradation of image quality when composing multiple adapters, the risk of introducing unwanted biases into the model, and the challenge of controlling the number of adapters per task to ensure high image diversity. Composing multiple adapters can lead to a decrease in visual fidelity, override existing concepts, and introduce foreign biases into the generated images. Additionally, the process of selecting relevant adapters based on user prompts may not always result in the desired outcome, as the system may struggle to accurately match specific tasks within complex prompts. Moreover, Stylus's masking strategy, which aims to control the number of adapters per task, may lead to challenges in managing the exponential number of masking schemes generated, potentially complicating the selection process and impacting the final image quality. Overall, while Stylus offers significant advancements in automating adapter selection and composition for image generation, these limitations highlight the need for further refinement and optimization to ensure consistent high-quality results across a wide range of prompts and tasks.